Hey guys, here we are, lesson 1W, practice problems with literal equations. We're going to be using word problems as well as some algebraic manipulation to, as we've got written here, write a mathematical expression or equation for the quantities described. We're not going to be solving, we're just going to be setting up equations, prepping you for calculus in the years to come. So let's go ahead and get started. I'd like to start with number 5 here, and then we'll go to number 8. So let's get started on 5. It says a number squared plus 8 is 89. So a couple of things here. When I see a number, I think of a variable. I don't want to use yellow. What the heck is that? Okay, so a number squared plus 8 is 89. So is typically represents equal, plus obviously is addition, and then you take the rest from there. So let's look at number 8. The square root of the quotient of a number divided by 4. So the square root of the quotient. So I've got the square root of division. Quotient means division of a number. I choose to use x every time I see a number divided by 4 is 5. There's our setup. Okay, let's scoot forward to 13 and 14. Okay, number 13. The sum of two numbers, x and y, so we're explicitly told to use x and y, and the term sum means addition, is 16. Write an equation for y in terms of x. So y in terms of x means I want to isolate y and have x represent its independent variable. So I'm just going to go ahead and subtract x. So y is equivalent to 16 minus x. So that is y in terms of x. Okay, number 14 says the product of two numbers x and y, product meaning multiplication, plus 4 is 36. Write an equation for y in terms of x. That means I want to isolate y and have x as the independent variable. So I would subtract 4 from both sides, giving me 32, and divide by x. Looks like I would get 32 divided by x. This would be true provided that x is not equal to 0. That would be a discontinuity, an undefined value, if you will. Okay, let's move to the next slide. All right, let's go ahead and start with number 17. So it tells me two numbers add to 16. You can choose to use whatever variables you'd like. I'm going to use x and y. Write an expression for the product of the two numbers in terms of only one variable. So I'm going to solve for y like we did in one of our previous problems here on the last page. And I want to write an expression for the product of the two numbers. So x times y, right? That will be equivalent to x times the expression that represents y, which is 16 minus x. So the product of the two numbers written in terms of one number, or one variable, would be the following. This would be our answer. So x times y, if I only know x, but I know that the two add up to 16, I could write my expression for the product of those two numbers as such. Okay, let's look at number 20. The difference between 9 times the first number and 3 times a second number is 21. So let's write this. It looks like 9 times the first number. Difference means subtraction. And 3 times the second number is 21. The sum of twice the first number and 5 times the third number. So sum means addition. 5 times the third number, I'll use z, is 95. It says write an expression for the product of all three numbers. So the product of all three numbers would be x times y times z in terms of only one variable. Now in this case, the variable that shows up in all three of these equations is x. Therefore, I want everything in terms of x. So I'm going to solve for y here, and I'm going to solve for z here, and then I will have all three of these terms in terms of x only. So for the first, if I subtract 9x and I divide by a -3, I will get 3x, I think that would be -7. Okay, and in the second expression, I would subtract 2x and divide by 5. That would give me a -2x over 5, and that would be +19. Okay, so now the product of the three numbers would be x times whatever y equals times whatever z equals. And now the product of the three numbers can be written in terms of x only. Okay. Let's move on to number 22. So scroll with me. Write an equation for the perimeter of a rectangle. Let's stop right there. Let's sketch a small rectangle. Let's call this length. Let's call this width. The perimeter of a rectangle is equal to 2 lengths plus 2 widths. Okay, and we got to tie these together, so it looks like the length is 6 inches more than twice the width. So the length equals 6 inches more than twice the width. Okay, so what I'm going to do, it looks like I want to write the perimeter in terms of only w. So I can plug this expression in for L. So the perimeter in terms of w only would be 2 L's, which can be written as 6 plus 2w plus 2 widths. So perimeter with respect to w would be 12 plus 6w. Do you see where I got the 6w? I multiplied 2 times 2, and then I added it to this 2. All right, and the 12 I got by distributing the 2 to the 6. So the perimeter with respect to w is 12 plus 6w, provided that the length is 6 inches more than twice the width. Okay, last question on this page will be number 24. The area of a circle in terms of the diameter. So let's relate the area of a circle. Area formula for a circle is pi r squared. Diameter, how does that relate to radius? Well, the diameter is 2 radii. Now, if I want to replace r so that I could have the area of a circle with respect to the diameter, because this formula right here is the area with respect to the radius. So in for r, I'm going to plug in diameter over 2. Okay, because if you look at a circle, the diameter is this length, the radius is this length, the diameter is twice the radius, therefore the radius is half the diameter. Therefore, the area of a circle with respect to the diameter will be 2, excuse me, mistake there. It will be pi times d squared over 2 squared, which is 4. So this would be our solution, or at least our equation, for the area of a circle in terms of its diameter. Okay, 3 problems I wanted to do on this page. Let's start with number 25. It says the area of a circle. We just worked with that, so we should be pretty comfortable with the area formula with regards to the radius, which is pi times r squared. And we need to relate that to the circumference. So how do we turn circumference, this formula, which is 2 pi r, into, or isolate r such that we can replace r to make this the area with respect to the circumference? So to get r, I would divide c by 2 pi. Okay, so r is equal to the circumference divided by 2 pi. Therefore, if r is equal to that, then I can do a direct substitution and I can solve. So the area of a circle with respect to the circumference would equal what we're going to get here. I'll simplify in a second. The circumference times pi over 4 pi squared. Kind of a weird formula here, but what we can see is that one of the pi's will reduce, so the area of a circle with respect to circumference will be c over 4 pi. So if you didn't catch that the first time through, I would reduce this pi with one of those. So I get c over 4 pi. Okay, next question that I'd like to do is problem number 29. So let's go ahead and shift our attention down there. A piece of wire, which is pi x inches long, is bent into a circle. So let's say there's no overlap. You don't have to twist it. It just end to end, it meets, right? So if I took this wire, which is pi x inches long, and I twisted it, that would become the circumference. So circumference would equal pi x. Pi x. What is the area of the circle in terms of x? Okay, this is interesting. So circumference is equal to 2 pi r. So that means if circumference is equal to pi x and circumference is also equal to 2 pi r, then pi x should be equal to 2 pi r. We can reduce out the pi's immediately because I would just divide both sides by pi. So that means x equals 2r, so r equals x over 2. Okay, so now we can find the area of this circle. Since we know the area of a circle with respect to r is pi r squared, and I know that r equals x over 2, then the area with respect to x would be a simplified version of the following, which would be pi x squared over 4. Awesome. Okay, I would like to do number 30. Number 30 is a unique problem. It says 500 feet of fencing are available to enclose a rectangular pasture along a river. So here I've got a river. Let's assume whatever our herding animal is, or whatever animal it is that we choose to put into this pen or pasture, will not jump into the water. So we use that as one of the edges of our fence line. Okay, so let's reread. 500 feet of fence are available to enclose a rectangular pasture. So what I know is that this length and this length are the same. Okay, and I'm actually going to call them width. This is the width, and this is the length of our rectangle. Okay, the river serves as one length of the rectangle, so only 3 sides require fencing. Express the area of the rectangular pasture as a function of W. Okay, so first of all, area of a rectangle will be length times width. But I want to write area with respect to W only. So I want an expression for W in terms of L. And the key here is the 500. Because it says that I have 500 feet of fence, that would equal L plus 2 W's, right? I would have to cover all that perimeter with that 500 feet. So I'm going to solve for L. L would equal 500 minus 2W. Right, I just subtract 2W from both sides, and that's what L equals in terms of W. So I'm going to input 500 minus 2W, and the area of the pasture with respect to the width would be 500W, I'm just distributing, minus 2W squared. Excellent. Let's move on to the next slide. Okay, we're going to start getting into some heavier algebra here. I'd like to do numbers 32 and 33, so let's start with 32. It says a rectangle is inscribed in a circle of diameter 12. So what it means to be inscribed is that the rectangle, each of its vertices are on the edge of the circle. That's an inscribed rectangle. I mean, it's drawn as good as I can, so at least by freehand. The diameter of the circle is 12 inches. Now I want to tie together the dimensions of the rectangle and the dimensions of the circle. So I'm going to draw the diameter from corner to corner. This is going to be 12 inches. And then what I'm going to do is I'm going to actually take this triangle out of the circle, just like this, where this is 12 inches. So I've pulled that triangle out, and it's a right triangle. It says express the area of the rectangle as a function of its width. So here what I've got is I've got a Pythagorean theorem situation. I've got length and width. Okay, I got length and width and length. So the area of the rectangle will be length times width. I want the expression for the area just in terms of W. So that means I have to come up with an expression for L. I might need a little bit more space there. We'll see. And then I'm going to multiply it by W. So when you see a right triangle, you should think Pythagorean theorem almost immediately when talking just about side lengths. If there's no angles present and you know it's a right triangle, you're probably going to work with Pythagorean theorem. So we've got L squared plus W squared equals 12 squared, and 12 squared is 144. If I want to replace L with W, that means I want to solve for L. So L squared is 144 minus W squared, and L would then equal the square root of 144 minus W squared. This is L in terms of W. So I can substitute that in for L here, and that's my expression for the area of the rectangle with respect to the width. I choose, just by preference, to write it this way. That's a squared. Make sure that's under the radical. That would be your answer. Okay, let's move on to 33. Okay, most formulas that we'll talk about that are foreign to you, or at least have been so long since geometry that you can't remember them, will likely be given to you. Okay, so in 33, it looks like the volume of a cylinder has been given to you. This is the volume formula for a cylinder, where capital B is the area of the base. Okay, and the area of the base in a cylinder is a circle, so therefore it'd be pi r squared. Okay, and the height is truly the height. And then over here, same thing. This is the same B. Okay, it's going to be a circle. Because if you think about it, right, the surface area of a cylinder is two circles, right? One here, one here. That's why I have two of those, two circles. And then the circumference times the height. So that's just the length around the base times the height will give you that rectangular space that kind of goes around. Okay, that wraps around, makes the sides of the cylinder. So in a certain right cylinder, the total surface area is 14 inches squared. Okay, so they're giving us S. That's 14. I don't really care about the inches squared right now. The units don't necessarily matter in the algebra here. Okay, area of the base we said was, let's see here, pi r squared. I don't know if we need that yet, so let's see what we got. Let's put in C times H. It says express the volume as a function of the circumference and the height. Okay, so let's get started on that. So if we want it just in terms of circumference height, the item that I want to rid myself of is the base, the area of the base. So I want to solve for the area of the base. So I would subtract C times H, and then I would divide by 2. Okay, that's going to give me B. So if I want the volume in terms of the circumference and the height, right? The circumference and the height, as it's two independent variables. And if it was area of the base times the height, I wanted to take out the area of the base and have it in terms of the circumference and height. So I'm going to sub that in. and I've got my formula. The volume with respect to the circumference and the height would be, I'm going to kind of simplify this a little bit, 7, that's 14 divided by 2, minus CH squared over 2. So that would be the volume of that right cylinder with respect to the circumference and the height. Okay, we're on to the next slide. I want to do numbers 36 and 37. An isosceles triangle has its base along the x-axis. So an isosceles triangle is a triangle whose two sides are the same length. So this side right here would be the base. This point right here is called the vertex. It's between those congruent side lengths. Okay, so its base is along the x-axis with one base vertex at the origin. So let's go ahead and plot this guy here. So it's got one base vertex there. It's got another vertex, looks like in the first quadrant on the graph, of 6 minus x squared. So this is 6. And this function here is y equals 6 minus x squared. Okay, so I've got an isosceles triangle where this length and this length are the same. Okay, so what I want to do here is I'm going to take this value, 0, 0, and I'm going to take this point, I'm going to call it x0. So what we know based on a isosceles triangle is that the x value here would be half of this x value here, okay, based on the symmetry of the triangle. So that would be x over 2, and then we would plug the output, which ends up being the height of the triangle, ends up being y of x over 2. So we plug x over 2 in to this function. So this point ends up being x over 2 comma 6 minus x over 2 squared. Right? That's the function's output at that x value. So that's x over 2 comma 6 minus x squared over 4. Okay, so now let's look at what the rest of the question is asking us. Write the area of the triangle as a function of the length of the base. We already determined the length of the base is x units. Okay, so the area of the triangle is 1/2 the base length times the height. Okay, and the height ends up being the output, right, of this point, this coordinate that lies on that curve. So that would be 6 minus x squared over 4. Now this would be the area of the triangle with respect to x. I'm going to simplify it slightly. If I distribute 1/2 x, I get 3x minus, that would be x cubed over 8. Okay, either of those two answers would be acceptable. The second is obviously much simpler, but both would be satisfying the needs of that necessary problem there. Okay. Let's look at 37, and then we'll move on to the last slide. Okay, so 37 says the point P is on the curve y equals x squared plus 1. Okay, so let's sketch y equals x squared plus 1. We've done that many times. It's just a transformation of that parent function. Okay, so it's got a y-intercept of 1. Looks kind of like that. So that's y equals x squared plus 1. Let's put a point P. Let's put it right here, and we'll say that that is x comma x squared plus 1, right? So that's whatever the x value is plugged into the function. Okay, so it says express the distance from P to the origin as a function of x. So I'm going to go ahead and draw a line here. So distance actually is derived from the Pythagorean Theorem. So if I resketch this triangle, I've got a base length of x, a height of x squared plus 1, and a hypotenuse, which I would call the distance. I'm going from 0, 0 to x squared plus 1. So I can either use Pythagorean Theorem or the distance formula. Either one is fine. They're actually the exact same thing in different forms. I'm going to take x squared plus x squared plus 1 squared, set that equal to the distance squared. So that would be x squared plus, if I FOIL this, that'd be x to the 4th plus 2x squared plus 1. And if I combine these like terms, I would get d squared is equal to x to the 4th plus 3x squared plus 1. So the distance with respect to x would be the square root of that thing. Okay, that's a pretty good one. But noticing that the distance formula really is just Pythagorean theorem will be helpful there. Anytime you get a right triangle, that's probably a good first guess. Okay, let's move on to the next slide. All right, here we are, last slide. I'd like to do problem 40, followed by problem 41. So here we've got an athletic field, kind of that track-looking field, with a perimeter of 1/4 of a mile, consisting of a rectangle with a semicircle at each end, as shown in the figure. Express the area of the field as a function of r. First, let's think about the area. I'm going to split this area into 3 spaces. Okay, the area represented by the 1 and the 3 actually represent a circle if you combine them. So I've got the area of the field is equal to the area of a circle plus the area of that rectangular space. Okay, so I'm going to come up with a formula here real quick to do that. Okay, so the area of a circle is going to be pi r squared, and the area of the rectangle. Okay, so let's call this r. That should be an r, not a v. Let's call that r. The area of the rectangle would actually be, its base length here would be 2r, and let's call its height L. So the area of the rectangle would be 2r times L. Okay, so that's going to be the area of the field. I want it just in terms of r. Right now it's in terms of r and L. So I got to use the 1/4 mile thing and some other stuff in order to come up with how I can eliminate L and just turn it into a function in terms of r. So let's speak first of all about the perimeter. So the perimeter is 2 L's. Okay, the perimeter is equal to 2L plus the circumference of the circle, right? So if I look at this, this is a half circle, and so is this, but together they'd be a full circle. And the circumference of a circle would be 2 pi r. Therefore, what I can do is I can eliminate p, because I know this value. So now I just have 2 variants, and I want to get rid of L. So I'm going to solve for L. So that means I'm going to take 0.25, subtract 2 pi. That gets me 2L alone, and now I'm going to divide by 2. I'm going to do something kind of slick here. 0.25 divided by 2 is 1/8. Okay, 1/4 divided by 2 is 1/8, and 2 pi divided by 2 is just pi. So L is equal to, oops, I forgot my R. There it went. So L is equal to 1/8 minus pi r. Now I can take my area formula, which was pi r squared plus 2RL, see that up here, and I'm going to substitute in 1/8 minus pi r. Okay, now what I have is area in terms of r. Let's see what we get here. I'm going to distribute and simplify. This would be plus 2r times 1/8 is r over 4. And then 2r times negative pi r would be negative 2 pi r squared. So if I combine these like terms here, the area with respect to r is r over 4 minus pi r squared. There you have it. That is number 40. Let's move on to number 41, the last one for this set of problems. Okay, I've got a square of side x that I'm cutting out of this cardboard box. Okay, so here's a cardboard box. And the cardboard box is 19 inches by 12 inches. And I'm chopping out an x by x square out of each corner such that I can fold up the sides. Okay, I'm taking those corners off, which will make it look like this. Not to scale, it's not perfect, but it would look like that. Now, along these perforated edges here, I would take these, and I'm going to do a little perspective drawing here, and I'd fold them up, creating this box, right? Where this height is x. Okay, now this length was 12, but I took away 2 x's, so that'll be 12 minus 2x. And this length was 19, but then I took away 2 x's, so minus 2x. So the volume of a rectangular prism is always length times width times height. Volume in this case, with respect to x, right, which is how much you cut out of it, would be its length, which I would probably call 12 minus 2x, times its width, which is 19 minus 2x, times its height. Okay, and as I do a little work to multiply this out, I would get 4x squared. I'm just foiling. And what would I have after that? Then I'd have minus 62x, which is negative 2x times 19, plus negative 2x times 12. That would be 24 and 38, which makes negative 62. And then 12 times 19 is 228. Then I distribute the x. That gives me 4x cubed minus 62x squared plus 228x. So there you have it. That's the volume of that box with respect to x. So if you made that cutout 2 by 2 square or 1 by 1 square or whatever you'd want it to be, it couldn't be 6, right? Because then that would cut off, that would be cutting it directly down the middle, and you couldn't, right? You couldn't, if you did a 6 by 6 square here, then you'd have no depth to your box, right? Or no width or no length. So there is a domain on this, which we're not going to cover, but some interesting stuff going on there. So hope this lesson made sense to you. The remainder of the problems are yours to work through and ask me any questions about. But that's it for literal equations 1W. The W stands for word problems and wow. So have a great day. We'll see you next time.